CSE142. I'm so glad to see you all here. So first of all, as an icebreaker, typically it's a good idea to tell you guys who I am. So I'm on way. As the photo shows, hopefully it's not too far away from what I look. This is probably like 10 years ago when I was still at UC San Diego as a postdoc. And I'm currently, like my full-time job is not too far away from here at UC Riverside, but because like I graduated here, and like if you have ever been to the inland area of California, that's not a place that's like survivable during the summertime. So summer is like UC San Diego is typically the place that I would stay for my summer. And so I have a lot of experience. Like I graduated from UC San Diego here, and as I told you, and something I show you here is that a few years ago I've been at Google working for TensorFlow Lite, so I have some idea about like what the industry looks like. And my personal research interest nowadays is trying to use ray tracing accelerators for a lot of different things, and using AI accelerators for a lot of different things and anything interesting. So if you are interested, we can talk about that later during the quarter. But fun fact, I was once, like when you are a PhD student or when you are a student, right? I mean, this is probably something that you still have in your mind, is that, do I really want to be a computer scientist? Right? Do I really want to be a programmer? Right? So this kind of question always have, you probably always have that in your mind. Same thing as I was a student. So I was considering, well, at some point, should I be, performing on a stage or something? And then, this is definitely not successful, so that's why I'm still here. And, I used to watch a lot of animations and do a lot of like cosplay style stuff. So like, if you see me previous years in Anime Expo, that's me, right? And recently, sometimes it's a life journey that you always want to know yourself better, right? So like recently, when you're on dating app or something, people typically ask you about what's the MBTI of yours. So last month some people asked me about that, so I took one. It shows me that I'm pretty consistent in a way that my research is computer architecture and my type is also architect. So now I want to know more about you, and to know more about you, we are going to use this polling app called Poll Everywhere, and you can scan this link through your mobile phone, or later on you can use the website, and the link is, the QR code is on the top left, and the link is on the top right, and you should be able to log in with your UCSD account. And now, please respond to this question.
What's your favorite CS topic?
All right, let's wrap up. Okay, so based on what you answered, I'm a little bit surprised about the answer though. Like a lot of people talking about system. Some of you talk about algorithms, some of you talk about security, some of you talk probability, cybersecurity. Okay, systems. Interesting. So let's follow up with another question. So why are you taking CSE142? Okay, 22 of you answer, so we can probably wrap up. Okay, so based on what you have answered, interesting. So a lot of you saying that you're very interested about system, but I'm sure that's probably not the right answer because, as you can tell, right, the main reason why you guys are here is just because it's the major requirement, right? So in fact, if you ask, these days I like to ask ChatGPT or Gemini a lot of things, like for a lot of guidance in my life, like. But let's ask about like ChatGPT and Gemini about like what are the most popular topic in computer science, and you can see, right, like, well, I'm a little bit surprised is because nobody talks about AI. Why? Right? Isn't that something true in your mind that you're interested about AI? Like, to be honest, like, you don't have to place me, right? This is not going to affect your grades. How many of you are interested about AI? Right, then why don't you put that in your favorite topic, right? Don't lie, right? So, and based on your answers, right? Most of the time, when we talk about computer science, when we talk about what to focus on in computer science, a lot of people are thinking about algorithm is the most important class, data structure is the most important class, system engineering, programming language, user interface, and nowadays like data mining, artificial intelligence. But whenever we talk about computer science, computer architecture, I know a lot of people, like, to be honest, a lot of people, because I graduated from a computer science major, I know a lot of my friends, they're doing about computer architecture. Right. Like if it's not required and nobody wants to take this class, I know for sure, right? So the thing is that, okay, why are we taking computer science, right? So if you ask ChatGPT or Gemini a different question regarding what are the important subjects in computer science, then computer architectures is actually in a very high ranking, right? So that's the reason why we want to learn computer architecture. And In fact, if you don't trust me, at least you should trust this guy. How many of you know this person? Here's Jeffrey Hinton. Who is Jeffrey Hinton? No? Okay, so Jeffrey Hinton, Young Kun, they are all considered as the father of deep neural network, right? So let's pay attention to the lecture he delivered in his Turing Award lecture on 2018.
But things like GPUs, or TPUs, allow you to apply a lot of computation, and they've made a huge difference. So really, the deciding factor, I think, was the increase in compute power. So I think a lot of the credit for deep learning really goes to the people who invented the big databases like KK Lee, and the people who made computers go fast, like David Patterson and others.
Okay, so at the end, what are the names he mentioned? David Patterson. Okay, who's David Patterson? You don't know who's David Patterson? How many of you check the website of the class? Of this class? How many of you know what's our textbook? How many of you who wrote the textbook? Who wrote the textbook? What's the name of the author of our textbook? David Patterson and John Hennessy, right? So here's the thing. A lot of the credits with deep neural network. Without computer architects, it's not happening. Seriously. Like, when I was really, really young, that was a time that people explored a lot of ideas about neural networks. That was early 2000. And at that time, people don't consider neural networks as something viable because it really takes a lot of time to perform inference and training with deep neural network. So it turns out, if you pay attention to the Turing Award lecture, you can still find this lecture on YouTube regarding the whole history about deep neural networks. And then you will know, in early 21st century, if you would like to write a paper about neural network, it's going to be rejected anyway, because people don't believe that's a possible idea ever. However, if you pay attention to what the research is about now regarding artificial intelligence, everything we are using deep neural networks, right? And the reason why deep neural networks have a chance again, it's just because computer architects. So computer architects, although a lot of people, your first impression about what's the important topic, you would never saw computer architecture as an option. But I want to say, computer architects, we are the hidden figures behind all the successful story of a lot of computer science innovation. So that's why, as a software engineer, we need to learn computer architects. And with the knowledge of computer architects, we can make the world, we can make our application possible or economically possible. So now, why should I care about computer architecture? So before we talk about why should we care about computer architecture, let's talk about what is computer architecture. So if you want to find out what is computer architecture, it's actually not that difficult in a way that you can find this information online from the dictionary, and it's actually one of the dictionary definition about what is architecture is actually the manner in which components in a computer and computer systems are organized or integrated. So that's computer architecture. So okay, so a lot of you think, I don't need to take computer architecture because I'm a software programmer, because I know the computer system very well. So now, I really want to test how good are you in knowing computer architecture. So we need to do some exercise. By exercise, I mean real movement. So now, what I'm going to do is that, how many of you watch those like game shows? Sometimes you have a lot of people guessing what is right, what is wrong, right? So we are going to do that. So For this question, if you think the answer is yes, on the left-hand side. If you think the answer is wrong, right-hand side. Move yourself. Come on, which side? Just pick one side. Okay, everyone seems to be moving on the left-hand side. Okay, sometimes we need more exercise. And the answer is yes. Now let's go to the second. On a SAM machine, programs with fewer lines of code will have shorter execution time. No. Do you want to follow the crowd? Well, sometimes the majority can be wrong, right? Like a lot of things, especially politics, right? We know the country might not be moving toward a direction, even though the general public saw it that way, right? But this time, I want to say, it seems like the majority is probably right, but you can have a seat. You have a seat. You can have a seat now. Yeah, if you get it wrong, you can have a seat. Go back to your seat. Yeah, so if you don't want to stand, you can pick the wrong answer. Now, let's go to the next question. On a SAM machine, an algorithm with lower computational complexities would, have shorter execution time when solving the same problem with the same input. Okay, so this is pretty much something that you would think after you get from CSE 101, right? Okay, but I want to tell you, they are liars. No, all right, you can have a seat. Okay, the remaining survivor. We have probably 5 more questions. The one who can answer all the 10 questions correctly, I will give you $20 Amazon gift card. So try your best. On a SAM machine, algorithm implementation with the same computational complexity with similar execution will have similar execution time when solving the same problem with the same input. Are you sure? Okay. No movement? Are you guys all set? Okay, thanks you guys for saving me $100. All right, 4 of you. Leveraging more bitwise operations in C code will make the program significantly faster. No move? Okay. All right. A few more questions. Algorithm is complexity is less important if we have rich parallel processing capabilities. In another word, complexity doesn't matter. Okay. 2 on each side. I know I'm going to save another $40, but which side is right? The answer is yes. Algorithm doesn't matter that much if we have rich parallelism. Okay. Now, Moore's law is currently discontinued. Moore's law is currently discontinued. Moore's law is currently discontinued.
When you say discontinued, do you mean just like straight up wrong or like?
What do you think? Is discontinued. What is Moore's law? What is Moore's law?
Oh, the idea that every however many years our computational speed doubles or something like that.
Okay. First of all, I want to say your interpretation about Moore's law is wrong. Would that change your mind? Okay. Moore's law is not discontinued. Okay. The smaller size of a transistor, the smaller power consumption of it. Okay. Okay. So the answer is wrong. Okay. Yeah, $20. Now, I still have 2 more questions. The most recent GPUs can match the demand for efficient AI ML training. No change? No change? Okay. Woo-hoo. Very last question. With GPUs, TPUs taking more roles, CPU performance doesn't matter that much in applications. What do you think about Intel these days? What do you think? You're going to stay there? Are you sure?
Yeah.
Do you really want your $20?
Yes.
You wanted $20? Okay, send me an email after the lecture. What's your name? What's your name?
Corey?
Corey. Okay. So, okay, so being honest, how many of the answers you guessed it?
Oh, like I think I maybe guessed on like 2 or 3. Yeah.
Okay, so here the thing, right? Like even Corey, he has like 2 or 3 questions that he have to guess, right? So we do have a few things that we need to learn in computer architecture, even though a lot of you don't think that's relevant to you. But if you review all the questions that I ask, they are actually pretty relevant to our software assistant development, right? So now let's go back to a very essential question. So for this question, I want you guys to grab a few people around you to discuss how does a computer execute your code in 3 minutes. Grab a few people around you to talk with each other. All right, how does a computer system execute your code? Do you guys have some rough idea about that? Like, what do you guys think? What do you guys think? What's your name? You just told him your name, but I didn't hear it.
My name is Simon.
Simon, okay, what do you think?
So basically, we will program in a high-level language,
Okay.
Python or C, stuff like that.
I'm glad that you categorize C as high-level language. Because a lot of people, when they talk about high-level language, they only consider like Python as high-level language. And the last time, a long time ago, I went to Google. Some software engineers call like C as low-level language. I'm almost like fight with them, but like okay, but you're doing a good job. Okay, C is a high-level language. So the definition of high-level and low-level language is basically the low-level language here means assembly language, and in programming language, whatever we categorize as high-level language is a language like C, Python, whatever. And what's the definition of high-level language?
Something that involves a lot of abstractions, so
Mhm.
that humans are able to code quite efficiently.
Okay, so by efficiently, Under what situation we are still able to code but not efficiently? I would argue that's not a good definition. Whenever you are not familiar with the language, that's not efficient, right? So what's the relative comparison to? So, or say like we say the low-level language is assembly, right? What's the fundamental difference between C and assembly, or Python and assembly?
So,
what's your name? Nick.
So I think in assembly, the difference is like assembly allow you to touch register.
Touch registers. Okay, so what does that mean to you?
That is, it gives the programmer more power.
More power? Is it more power or? So, okay, what's your name? Alessio? Okay.
Would assembly just be more like not understandable by human because
Is it really not that understandable by human beings? Like I can see like add, register, 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 right? What do you think? What's your name? Judy.
I think the difference between the two is that, like you said earlier, there is abstraction. So like we don't know for C, obviously we don't know like where things stored, or like we have also more access to operations as if we were using assembly, we only get to use like very bare minimum operations like add, move, sub. Like we don't really, and then obviously in C we have so many different operations we have access to. So.
Okay, so I would say for high level.
Can I try?
Sure.
Like you said earlier.
What's your name, by the way?
Leah.
Leah.
Yeah.
Okay.
Like you said earlier, assembly interacts more directly with registers. I would say maybe the difference is low-level languages have more direct control over what your computer is doing and like what the actual thing that computer is executing, while like I mentioned, this abstraction. High-level languages have to eventually translate that into something that the computer does, while low-level languages like control what the computer is doing itself.
Okay, so low-level language, you have more control, or on the other hand, you have to explicitly control what the computer is doing, right? So based on what Simon just said, why high-level language is more efficient from the programmer's perspective? Judy?
I think it's because like we don't have to deal with the nitty-gritty of the architecture itself.
You don't have to deal with the architecture itself, or at least like, or on the other hand, you don't have to explicitly step by step tell your architecture, tell your processor, tell your computer what to do, right? So for example, like in many cases, like I hire like, okay, saying that, well, let me find a good example. Okay, so let's say like, sometimes when I go back from the airport, I would take a Uber, right? And if I want to take the Uber, right, it's pretty simple, right? I just use the app, tell where is my destination and where I am, and I got to my direction. I got to my place, right? So it's all about just like putting one request, send me back to my home, and I'm done. But thinking about, you have an Uber driver. The Uber driver has no knowledge about San Diego. And the Uber driver doesn't know how to use GPS. The Uber driver would require you to tell, should I turn right here? Should I turn left there? Should I go to the highway? Should I go on this entrance? Right? Then that's not very convenient. You will feel like, okay, give me the car. I will drive by myself, right? So same thing, why we want high-level language, because it's giving us a lot of freedom in giving us, release us a lot in programming, right? Okay, so now we have high-level language. We wrote a program in high-level language. Then what happened? What's after? What's after the high-level language? I wrote a program. hello world. And then?
This combined into lower language.
Okay, so again, right, high-level language, that's for us to read, but the computer itself only understands the low-level language, which means the assembly. And one thing that you didn't mention is that assembly language is actually a one-to-one mapping to machine instructions. So that's why we have to deal with registers. We have to deal with those real low-level operations because they are exactly what your machine knows, right? So low-level language, or say machine instructions, is what's after the high-level language. Okay, so then with this compiled instructions or compiled program, what are we going to do? Well, the compiler already compiled the program, right? So now we have the program. First of all, where is the compiled program? We compile something. Where do we put that?
Well, I mean, it's not really up to us. It's kind of like the hardware decides that for us.
Okay.
It's like somewhere in memory.
Somewhere in memory. Okay, you mentioned something memory. Okay, so the compiled program would be the memory. Then what's after? Corey.
I believe what happens is that the computer needs to take that compiled code and turn it into an entire process. So like, yeah, that involves loading it into memory.
Loading it into the memory, and then?
Allocating some pages for like the stack.
Okay, that's still about memory, right? And then what after?
Okay, so then you have your entire process, and then it gets the operating system schedules it using a scheduling policy, and then it just waits for its turn to run.
Okay, when it's my turn for running that process, what the processor would do. What's your name? Rachel. Mitchell. What do you think? Processor turn into bytecode. What do you mean by bytecode here? Okay, so what if the machine instruction itself is already ones and zeros? Then what do we do? What does the processor do? Bingo, right? So the CPU would take the instruction line by line and execute that, right? So in the past, we have learned a lot of things. One piece from the operating system, one piece from the CSE30s, one piece from CSE001, I guess, if there is still such a class, right? Some piece from CSE100. But we never put everything together. So computer architecture is a class that would put everything together. So right now, let's look into that. So first of all, I would show you a demo. So in this class, we are going to use Jupyter Notebook a lot. And for this Jupyter Notebook, what I'm going to show you is that now I have a program which is pretty simple. As you know, like this program is declare an array. And for this array, what I'm going to do with this piece of code, I'm just like summing up everything together. And in Linux or any kind of Unix-based system, you can use like programs like GCC to compile your code. So here I'm going to use GCC to compile my code, and now I use another program called object dump. So the program object dump is trying to disassemble what's inside this executable called simple. So as you can see, this is exactly what's inside your program, and there are tons of instructions like add or like rotation or something that we cannot really understand, right? As we said, we don't want to program at this level, right? But you can see this is exactly like machine instructions, and they have their own meaning and control what a computer is going to do with that. And typically in your program, you will have two main sessions. So one session is called like the text section, or say the instruction section, which like here, we can see this bracket, it say this is the main function. So whenever the program starts, it will locate. So you will have some instruction that's set up where the beginning of the main function is, and then you jump to that main function and you will do a lot of operations like push, move, and jump, right? And at the end of the program, there is also a data section. So this is, sorry. Let's see. Do we see the data section? Wait, where's my data section? I saw it. I saw it somewhere. Is it at the end? Okay. Oh, okay, so here's the data section, right? So sometimes the object jump doesn't interpret it perfectly, but here you can see there is a bracket A, right? So you can probably guess this is where the array A starts, right? And then if you see the content here, there's a 1, there's a 2, there's a 3, there's a 4, right? So the array data is also embedded in a compiled binary if you declare that in advance, right? So for this like simple program, right, what happened is that you can imagine, even though we have high-level languages, everything has to be turned into low-level instructions, and these low-level instructions, they may either perform arithmetic operations or memory operations or logical operations or control operations. But the main purpose of this text section or say instruction section is to control what the machine or what the processor is going to do. And then for variables, we would allocate them into data sections, which would contain the initialization values of this array, right? So this is what a program really looks like. So the computer doesn't understand this at all. It has to be compiled or translated into machine instructions like that. And why do we need to compile our program in this way? As many of you know, because we are running our computer applications using this von Neumann architecture. So what is von Neumann architecture? So John von Neumann, he defines a reprogrammable computer should look like this. So what does that mean by von Neumann architecture? So when someone say von Neumann architecture, here are the things that you should have in mind. 3 different types of components: processor, memory, and now storage. So in the very beginning of the von Neumann architecture proposal, there is nothing mentioned about storage, but can you imagine that your program vanished after you power off, right? So at the time that von Neumann doesn't mention the storage is because at the time of John von Neumann, there are things like punch cards, right? So it's actually non-volatile. So I want to say a lot of memory, they start with non-volatile and then it goes to volatile, right? So now the non-volatile memory specifically, we categorize them as storage. So how do we use these different types of components? It's like this. First of all, when you compile your program, we put them in the non-volatile storage. And each program, as we just showed you, it has text section, contain instructions. It also has data sections, contain data. And whenever we want to execute a program, the operating system or your microcode or firmware code will load the program into the memory. And regarding this, like Corey just mentioned, there is an abstraction called process. So in operating system, the definition of a process is a running instance of a program. So what does that mean is that a program may have multiple copies of this in a memory. And each of them is considered as a process. So process is a running instance of your program. So when you want to create a running program, you may need to create a process. And again, what's necessary in a process is that the process needs to contain the instructions and the data for this running program. And what's happened is that in your processor, there is a specific spatial register called program counter, which would tell us, now, I want to start executing this program. Where in the memory do I have the upcoming instruction to execute? And then what's happened is that based on the instruction count, the program counter, it would fetch that specific instruction from the memory and then look into the content of that instruction, decides what ALUs, what operation should the processor doing. And once we are done, and sometimes if the instruction needs to access data, that's when we need to trigger access to the data. And then once we are done, we can move to another instruction afterwards. And the beauty of volumetric architecture compared against other architectures is basically you can change the function of your computer simply by loading different programs into memory. So like the same machine, right? Typically during the night, you would use it to play online games, right? Watch YouTube videos, right? But when your parents come in, it's definitely something else, right? Jupyter Notebook, right? How this magic happens? Just because we have volume architecture, right? When you hear someone is stepping towards your room, you know Alt-Tab. And I can change the program. So when they open the door, right, it sounds like, okay, my kid is really working hard, right? And getting more desserts afterwards, right? Something like that, right? So the beauty of volume architecture is that by changing this memory content, simply changing this memory content, I don't have to reconfigure the hardware. The computer can react totally differently, right? So the same machine, the same set of hardware will work for many, many different things. So that's why volume architecture is so popular. So if you have C code, right, you have to compile your code and it will generate machine code like this. And when you want to execute that, you will use the same way that we just described, load this program into the memory, and then the processor execute that line by line. And if you have a program like Java, you still have to compile it. However, what you compile into is something called Java bytecode. And this Java bytecode is still something like a machine instruction. However, this machine instruction is not the native machine instructions that your machine understands. You have to go through a Java virtual machine to interpret that into the real instructions that these machines can execute, and then you can run the program. And most of you are now saying that, okay, I don't program at this level. This is the programming language I like, right? So, but even with Python, you still cannot have the processor directly running those Python lines. You need an interpreter which translates your Python code into machine instructions, and then this machine instruction will be dynamically loaded into the memory during the runtime. And again, the same process of volume architecture holds, right? So that's the whole idea about volume architecture. And as you can see, no matter what programming language you are using, you need a processor and memory. So that explains why processor and memories, they are everywhere. So I don't know how many of you are familiar with the hardware. How many of you ever assemble a computer yourself? No? Okay. So, I assume yes. I assume that's the case, right? So that's why I brought this set of stuff. So, okay. So let me show you. So be careful. I think they are still like functioning before I took them here. So this is a motherboard. So as you can see, typically, right, in your computer, a computer is probably something like this. Like you have, let's see, oops. Okay, right. So if you can assume that you have a box, right? And this is what you would look like in your computer. Here's a video card, right? There are some audio outputs, and that's the USB, right? So, and on the other hand, this is what you will see. So there is typically a heat sink like this. And under this heat sink, you will find out there is a microprocessor, or say your CPU look like this. So this is an Intel processor. You can pass along. Thank you. And then a lot of you, and then where's the memory? The memory is right here.
right? And typically, our memory are a few chips that we assemble them in a solder in a DIMM, right? So this is a DIMM. And a lot of you might be asking, okay, most of the time, I'm not using, like for AI, I use like GPUs a lot, right? So this is a low-end gaming GPU that I have, right? So GPU, again, we have, because it's pretty hot, so they would typically have his sink. And under this his sink, you will see video like a graphic chip here, right? So you can pass it along. And this is a motherboard, and the motherboard has a lot of sockets. So here's a socket for memory, here's a socket for CPU, and this is the socket for your solid state drive. So if you have never seen a motherboard, that's it. And also, you know, the motherboard that I show you is a few generations ago, and this is like one of the latest generation of the Intel processor. So the one just recently died, so that, well, the one that I show you that is passing along, that is functioning, and this one is dead. So this is a Intel processor, 12th generation, and it's a different shape. So it tells you that the CPU doesn't have to be square, like this one is rectangular. Right? So you can pass this along, and be careful, there are some stuff like right there. Okay, so that's the motherboard, and as you can see, the motherboard has a socket for processor, has socket for memory, and also for peripherals. And you might think about like server is more powerful, but the server that you will be using for this class, they are just different, slightly different in a way that we have more sockets for CPUs and more sockets for DRAM, and that's about it. CPUs and DRAMs, they are still everywhere. And like mine, MacBook Pro, it's also a processor. It's also a combination of processor and DRAM in a single chip. But it doesn't mean that we don't have DRAM. It's just because we use like multi-chip package to make them a single package. But we still need processor and DRAM. And the same thing for iPhone, right? So this is my iPhone. It's still a single chip package with both processor and DRAM. And PlayStation 5, we need processor. We also have a processor and also a few chips. They made it like a circle style as with DRAM, right? And like some of you might be thinking about like, okay, how about Tesla, right? So Tesla is also like this. So this is the main board of Tesla. You have two Tesla processors, and the reason why they need two is because typically for machines, we want redundancy, right? So they have two sets of the processor, two sets of the DRAM. Doesn't mean that they are parallel processing just for redundancy, right? So even for a Tesla Model 3, it's also a computer, right? So processor and memories are everywhere. So that's why in the very first question, what everyone answered about this question is actually true. We need processor and memory are everywhere. But the fundamental reason is just because every machine is an implementation of the von Neumann architecture. So that's why they have to be everywhere. So a lot of you think about, okay, once I'm done with the algorithm, I'm done with my journey as a software programmer, because algorithm by like implementing the most efficient algorithm, then I'm done with being a programmer who can write a code that runs faster. Is this true? Right? So a lot of you probably don't believe the answer that I show. So I want to show you something in a demo. So the first demo I'm going to show you is this. So for those algorithm geeks, tell me, if today I don't run this sort, what's the algorithm complexity of this code snippet? If I don't run this part, what's the order of it? What's the order of this if I don't run this part? Is this question that hard? What's the order of that? Order what? You took CSE100, right? Who is your teacher? Let me talk to them. What's the complexity of this? What? ON, right? Okay, now, what's the best sorting algorithm you can come up in mind? What's the complexity of that? Order and log n, right? So what does that mean is that if today I run a sort, the code snippet would have a complexity of order and log n. If I don't run a sort, the complexity would be just order n. So if you took CSE101, you will think I should not execute this sort. Agree? Okay, but let's take a look at the demo. So here I have a program which implement exactly the code here. So this is the second loop, and the whole code contains two parts. One is the first loop, and the other is the second loop. And for the second loop, this iterations substitute that 1,000 because I want to control the number of 1,000 there. So now, let me run a program with sorting. So with sorting, it takes about 0.170 seconds to run, right? You don't feel the latency. Now, the same size, run it without sorting, it takes 0.6. So even though it sounds like, okay, adding sorting is adding some redundant operation, adding a complexity to the program, it's actually faster. Now, some of you don't believe this because you think this is a smaller number. Let's try a large number. Okay, so let's try a large number. So when you see the large number, it still holds the same, right? Without sorting, 0.3. With sorting, 1.1. So what does that mean? Are you ready to throw your algorithm textbook? Complexity doesn't really reflect the real performance. So that's why on the same machine, programs with fewer lines of code would have shorter execution time, and algorithm with lower computational complexity will have shorter execution time. They are both wrong. Now, let's talk about the second demo that I'm going to show you. So for these two pieces of code, what about their complexity? N squared. How about the right-hand side? Are they the same? So they are both the same, right? So they are both order n squared. Now, how about their performance? Let's run it. So here's the code that I have. Left-hand side, right-hand side, exactly look like what you see. And now let's run it. So let me recompile it, and then let me run it with 16K by 16K matrix. And I run, what's the left-hand side? Okay, I go with I and then J. So this one takes 6.1 seconds. And if I go to another order, it actually takes 9.2. So these two loops, they look the same. Complexity the same. They are doing the same thing. They generate the same result. However, the left-hand side has significantly better performance. So, complexity, what a trash is that, right? So even with the same machine, the same algorithm different algorithm implementation, the same computational complexity doesn't work. It doesn't predict the performance for us at all. Now, bitwise operations, right? So the left-hand side is the stupid code. The right-hand side use more bitwise operations, right? And a lot of you might think about, well, especially a lot of the very old engineers, they think about the right-hand side of code looks better. But let's see, do we really need to write our C code that in that nasty way? Oops. Okay, so let me run this pieces of a code. And then for this piece of code, I'm going to run this swap instance for this amount of times. And as you can see, there's almost no difference, right? So why bother writing your code like the right-hand side? It's not faster, right? So this is not right. Now, the fourth demo I'm going to show you is that saying that if we can run sort on GPU, which has thousands of cores that can run in parallel, is an implementation of machine architecture with rich parallelism. And I have two sorting algorithms. One is quick sort. As many of you know, the algorithm complexity is order ln n log n. And I also have another algorithm which is called Betonic sort. And this is the algorithm of Betonic sort. If you check the algorithm complexity, it's actually n log square n. So the right-hand side has significantly higher computational complexity. But let's run it on the GPU and see what's going on. So this is the quick sort, Dakuda, and this is the Betonic sort, and it implements exactly the loop that I show you. And now let's run the Betonic sort. So sorting, this is like 256K numbers. It takes 0.1 seconds. And now let's try using quick sort with the same amount of numbers being sorted. And to save our time, I'm also running larger instances. Okay, so as you can see, right, if I use quick sort, it would take 8 seconds, significantly more, right? And now, if I run it with 512K numbers, let's see how much time it would take. So if I run it with 512K with quick sort, how much time it would take? Okay, so with quick sort, it would take, you know, this is an n-log n algorithm, right? So if it's twice more, right, supposedly it's only going to be 1.5 times longer, right? The 1.5 times is probably 12 seconds, right? But apparently we are waiting for more than 12 seconds, right? So another evidence that computational complexity is not trustworthy. And in fact, it will take 33 seconds. Take a look of Betonic sort. Hey, come on. I double the amount of numbers. However, it's still about the same time, right? So what does that tell you? If you have a machine with very rich level of parallelism, then complexity doesn't matter, right? Why bother taking your algorithm class? Do you feel better now? If you don't ace in computer algorithm, you still have a bright life. And I would say your life is even brighter because you don't have the restriction about thinking about algorithm complexity, right? So now the first takeaway of this class is, why are we taking CSE142? Because algorithm complexity doesn't matter. Doesn't work very well on real computers. Now, okay, we are living in a world with volume architecture. And volume architecture, as we know, is based on processor and memory. And processor and memory, they are made with transistors. So it really matters a lot for the Moore's law. So the performance, or say what we can deliver, is highly dependent on the Moore's law. So based on some of your early answers, I do believe we need to recap on Moore's law. So I'm now going to give like a short, like a Reels or say like TikTok style presentation on Moore's law. So what is Moore's law? So if you take a look at the paper, it's basically telling you about integrated circuits. They are increasingly popular and they are very well established nowadays. However, and also they are getting more and more reliable, and they can be made really, really small. And how small they can be, if you look at the trend, they are easy to manufacture, and we are getting it smaller and smaller in a way that every 18 months we are making it smaller by half. And heat is a softball issue, and designing ICs can be easy. So that's the whole paper about the Moore's law. Believe it or not, you have finished reading it. So here, do we mention anything about performance? Nothing. The Moore's law is only about this. Transistors are made smaller and smaller every 12 to 24 months. And in fact, if you take a look, since the Moore's law paper is published and now, this is the density of the chip that we have. It's still surviving very well. It's still surviving very well. We are still able to make chips smaller and smaller. But does that meaningful? Is that meaningful? The answer is no, because even though the chip is able to be smaller and smaller, but our performance is not increasing a lot. In the past 10 years, based on Moore's law, our chip is probably 32 times smaller. But the performance we get is only 5 times faster. And here's the curve of Moore's law. So the performance is not growing with the improvement of Moore's law. And some of you might be thinking about GPU is doing a better job. But if you add GPU in this plot, it's not really doing a lot of bad. It's not doing any better than the Moore's law in a way that in the past 10 years, we barely managed the performance to go up by 21 times, which suppose Moore's law should give us 32 times. So some guy, some CEO, they keep saying that we surpassed the Moore's law. Our architecture follows the Moore's law. I don't want to comment which company is that, but based on the coloring, it's probably not too difficult to guess. He is a liar. Okay. And the other thing is that, okay, 21 times seems a lot, but where's the demand? If you look at the AI demand, it's actually 43 million times more than the past 10 years. So the current computer architecture is falling significantly behind the application demand. So even with the GPUs, we still have a lot to go. So that's why we need to learn computer architecture, right? So processor memories, they are essential to all the applications, including the ones that you care about. But the thing is that because DNOS scaling discontinues, and later on when you do your reading, you will know that the DNOS scaling means the per transistor power consumption. It did not go down with smaller transistors. So we are not able to make our chip smaller but more performing. Question?
I have a question about the graph on the previous slide.
Mm-hmm.
Could you explain what the y-axis?
The y-axis is the giga floating point operations that is necessary. For the red line is the necessary floating point operations we need to support per second to train a model within a week. And for the for the green and the blue, they mean the flops that each processor can deploy, can support at any moment. Okay. So regarding memory, we are also having a huge gap between processor performance and the memory. So that's also another issue we have to address. And it's even worse in a way that if we rely on GPU, we have to move a lot from the memory. So everything would eventually be bottlenecked by the memory. And not everything can be done on the GPU. So even though we have GPUs and TPUs, CPU performance still matters a lot, right? So why are we taking CSE142? Because we have to rethink about programming as computers become more parallel, heterogeneous, and application specific. And to be short, why we want to learn computer architecture. So the thing is that a lot of things, I don't know how many of you saw this before. You watched this animation, right? I like to guess that. And you probably have an answer now, right? But the thing is that a lot of cases, we don't really understand what kind of beast that we are dealing with. If you don't understand what your Pokemon is doing, you cannot do the right thing, right? So a lot of cases, we think this is what a computer looks like. But in fact, you don't understand your computer at all, right? Because you think, I have a Pikachu, but maybe Minik is the one that you have, right? And if you don't do the right thing, you are not going to make the right choice when you battle with your enemies, right? So, so this is why we need to learn computer architecture. So now I'm going to talk about the vision statement. So we want to be, so for after this class, we hope you guys can become programmers who write efficient programs that can save time, power, energy, and carbon footprint. And our mission is to use the knowledge of computer architecture and the general guidelines to identify performance problems, design solutions to optimize program, and fulfill the real world demands. So that's what we hope we can achieve after taking this class. So let's talk a little bit. So for this class, we are going to cover 4 types of topic. The first week, which starting from now, we are going to talk about performance, and then we are going to talk about memory, we are going to talk about processor and parallelism. And you can see this tentative schedule online through our website, and you see we have aligned our topics with those directions very well. And now I'm going to talk about what you care most about learning experience, and you probably would figure out our learning experience is something different from what you have been experienced before. So I don't like watch news a lot these days because they are typically very boring. Like my grandma, when she was alive, she typically would watch this and get sleepy, right? So I don't want my lecture to be like that. So what I want to do is like the game show that we had before, right? So like, you know, like you are just like one of the participants, right? So the way how we are going to do our game or our lecture is using this method called peer instruction. So before the lecture, you will have to read. So the reason why we want you to read before the class is you cannot imagine yourself participating in a game show without any preparation, right? If today I say, hey, congratulations, you are elected to join like Ninja Warrior. What do you think? I need to go to the gym, right? At least, right? So the thing is that you have to do some preparation. And then during the lecture, I will bring some activities for you to individually think, and then group discussion, and then doing the whole group room discussion, pretty much like what we have experienced today. And we will have reading quizzes, and there will be 33% of your grades, and you can find it on Gradescope. And during the lecture, you will use Poll Everywhere, which you have already used today, and I saw you successfully put your answer in. And this is also the way how we log your participation into the class. So Poll Everywhere or say peer instruction, it counts as one assignment in our grading criteria. And I don't require you to be here all the time because I know we have a lot of things going on in our life, right? Sometimes I'm sick, sometimes I'm just feel like mentally sick. For example, I don't want to show up in the class. I'm an introvert. I don't want to talk to people, right? So 50%, I think this is a very low requirement, right? 50%, and you can get full credits for that. And we also have assignments, and for the assignments, we made it easy for those of you who also take CSE142L, is that it's the same assignment, and so that if you are taking these two classes together, it won't like add you too much time to get credits for another class. And the reason why we want to do that is because I know some of you probably in your graduation criteria, you still need 142L. And based on my understanding, my information, this is going to be the very, very last 142L you can ever take in CSE department. So if you need that to graduate, this is the last chance. And logistically, we have 3 grading criteria: reading quiz, assignments, exams. They are all equally weighted. And we are going to use Trident Testing Center for midterms and finals. So they are all computer-based. And this is my first time using this service, so we will figure out more how to schedule that later. But this is how we are going to do. And assignments, we will drop the lowest one. And for reading quiz, we are going to drop the lowest 2. And for exams, we will take everything as an average. And more information, you can find us out on our course website. And this is me. And for this class, we cannot be successful without other people to help. So we have RTA. Do you want to talk a little bit about yourself?
My name is Moyan, and I'll be a team for So my office hours is on Friday, 9 to 11 a.m. So if you get come to
Are you looking for partners for that?
yeah. If you guys want to see me here, I think you can still see that. I'm not pretty sure because last week we can see that.
Okay.
So not pretty sure right now, but you can try.
Okay, so we have one tutor. So his name is Andrew, and apparently he's not here. And he will do most of the office hours online on Zoom on Saturday and Sunday, which is a great time for you guys. I know a lot of you like Saturday and Sunday because you get more flexibility. And if you are a Pokemon geek, talk to him. And we also have Owen here.
Hi, I'm Owen. I'm a tutor for 142L. So we're having office hours on Thursday and Saturday. I think we did Friday, actually.
Okay, Friday.
Actually, I'm not sure.
Okay.
But yeah, I think I'm the final tutor for 142L like ever.
Yeah. Yeah. You had matcha? Okay. Boo. Okay. So, but you know, we have a lot of things going on. So subscribe to our calendar. That's how you find us. So discussion session will be led by our TA, and that's where if you need hints for your assignments, right, or you need some support, or you have some concept that you don't understand what I'm talking about, maybe the TA would do a better job than me, right? So most importantly, subscribe to check our website. We have all the information, and my habit is that I want to take a photo with everyone that I taught. So I hope at the end of this summer session, we can take a photo together. And before you leave the classroom, first of all, log into Piazza for discussion. And we perform our assignments on Data Hub, our own Data Hub, not a Data Hub at UCSD. And we have Grayscope and make sure that everything works fine. And the most important information, they are all on our website. And there is a reading quiz due tomorrow before the lecture. So log into Grayscope as soon as possible and check our website. Other than that, enjoy the rest of your day. I will see you tomorrow.